Hello and welcome to another walkthrough of AQA AS level physics paper 1 74071 2024, and we are going to do it together, and I would request you to stay with me, and I'm making this walkthrough especially for those students who are going to be appeared in May-June 2025 session. So before going into details, please, I have a kind request to subscribe and like my channel because I really need your support. It will be very helpful for me that if people, hardworking people like you, are like appreciating my efforts, then I'll be very happy. Okay, so let's let's start. Question number one: an electron neutrino interacts with chlorine 37 nucleus to produce an argon 37 nucleus and an electron. The interaction is represented by the equation VE equals 37 chlorine and 37 argon plus E. Explain with reference to appropriate conservation laws why the electron is emitted in this reaction. So it is quite obvious that we have to keep the moment charge and lepton number to conserve charge number and to conserve lepton number. Okay. How? Okay. Please hold on. Let me save this one. Okay. So how? You can see that on the left hand side, I'll write it here. You have numbers actually electron should have. Therefore, as well. Lepton. This neutrino, electron neutrino, VE means electron neutrino, right? So that is lepton, and here you have a lepton number of 1. Okay. And for the atom that you have, it's like a big atom, so you don't have a lepton number for this. You don't have a lepton number for this. And this is electron, and electron is a lepton. So in order to conserve the lepton number on both sides, there must be an emission of electron. So for the lepton, we have 1 and 1 on the right hand side and left hand side. And for the charge, we also have that. Okay. So therefore, the answer to this question is to conserve the lepton number and charge number. Calculate the specific charge of the argon 37 nucleus. Okay. So what is specific charge? Specific charge is defined as charge per unit mass. Okay. Charge per unit mass. Now, what is the total charge of the argon 37 atom? Total charge of AR37. It is actually having how much protons? 18 protons. Okay. So 18 protons. So total charge is 18 times. And charge of one proton is 1.6 into 10 raised to the power minus 19 coulombs. So that makes up to 2.88 into 10 raised to the power minus 18 coulombs. Okay. And how much is the total mass of the argon atom? Total mass, protons plus total protons. Okay. Total protons plus total neutrons. Or simply we will say it is 37, right? So, and mass, or like the mass of one proton and one neutron can be considered as 1.66 into 10 raised to the power minus 27. Okay, so we will just write 37 1.66 into 10 raised to the power minus 27. And what is 1.66? It is actually mass of one proton or neutron. It is like 1.673, something like that, and 675. We have like fourth decimal number changed for proton and neutron, but we will just round it off and make it like same for both, just to make our calculations easy. So the answer to this question here now, 6.14 into 10 raised to the power minus 27 kg. Now this is your total mass, right? And this is your total charge. And all you need to do is just to divide these two numbers, right? So this is equals to this. Now specific charge is total mass over total charge. So this is going to be total charge over total mass, sorry. So 2.88 times 10 raised to the power minus 18 over 6.14 into 10 raised to the power minus, wait, let me calculate it. Where's my calculator? Okay. 37 into 1.66 into 10 raised to the power minus 27. 6.1 minus 26. Okay, so that is actually 26. I just checked. So you will just put 26 here. And the answer to this is 4.69 into 10 raised to the power 7 coulombs per kg. Okay, right. So let's move on to next part. In a different interaction, the argon-37 nucleus interacts with an electron. Figure 1 represents the interaction of a quark in a baryon of the nucleus. Deduce the exchange particle and the effect on the baryon. Give one reason to support each answer. Well, I will say that here the exchange particle is W plus. Okay, and why I'm saying it, because whenever you have electron and neutrino involved in your interaction, it means it is a weak interaction. And for weak interaction, you usually have boson. Okay, and why boson? Because it takes away your additional charge or balance out the charge. So exchange particle here is W, and we will say that weak interaction is the reason, because electron and neutrino is there. Okay, and what about the effect on baryon? Of course, when electron is coming and hitting baryon, for example, baryon can be neutron, right? And the structure of neutron is UDD, right? So for example, if an electron is coming and hitting it, it may turn into proton, right? So the flavor of one of the quark has been changed and it is turned into proton, and because of that, it has a positive charge, and that positive charge will be taken away by W boson, right? W plus boson. Therefore, it is W plus, not W minus, because the additional charge has to be taken out by the boson. Okay, so we will say that effect on baryon. We will write that a quark inside baryon can change into another quark. Okay, right? Or we can say it can change its another quark or flavor, like down can be converted into up. Okay, and when it happens, the additional charge is taken away by W plus boson. Okay, right. Any problem? No problem. Okay. 1.4, the argon-37 nucleus decays into a stable nucleus. Describe the nature of the forces that act between nucleus and how these forces can maintain nuclear stability. In your answer, describe the forces of repulsion and attraction that act between nucleons, exchange particles associated with these forces, and the role of these forces in keeping the nucleus stable. Okay, so first of all, if two protons are coming close to each other, they are going to repel each other, right? Right? This is called electrostatic repulsion. Electrostatic repulsion. And who is going to overcome this electrostatic repulsion and force all the protons to stay inside nucleus, keep and calm? No fight. So that is actually strong nuclear force. Strong nuclear force is there to overcome this electrostatic repulsion, right? Right? So you will have two kinds of forces, electrostatic repulsion between protons, and strong nuclear force, SNF, is there to overcome this electrostatic repulsion, right? And you can say that its range is about, not here, here. The range is about 10 raised to the power minus 15 meters, right? And the range of electrostatic force is longer range than S and F, okay? So that is the answer to the first, the forces of repulsion, okay? So these are the forces, repulsion, okay, and attraction. Well, SNF can be attractive and can be repulsive, but here we will just say that it is an attractive force just to overcome the repulsion between the electrostatic force, okay? Now, exchange particles associated with these forces. So let's talk about that in a different color, okay? So I'm gonna write. So first of all, you have how many forces? Two. One that is SNF and one that is electrostatic repulsion, right? So the particles for this are gluons, Okay, and gluons are kind of particles. These are necessary to bound the quarks, okay, inside baryon. Okay, so for example, if you have a proton and you have up, up, and down, so these are bound together like this with the help of gluon, you can say. Okay, so electrostatic repulsion is I made it a little bit dirty, so let me make it like clear and concise. So for example, this is U, and this is D. So the gluons are going to be like that. They are like, so these are the particles which are bounding all the quarks inside a proton, which is a baryon. Okay, so now electrostatic repulsion. So for electrostatic repulsion, we have virtual photons. Okay, and what are virtual photons? These are the particles, virtual particles, which mediate the attraction or repulsion, right? You can say electromagnetic forces between what? Of course, between charged particles, because electromagnetic forces are between charged particles, not neutral and not neutron and proton. They don't have the electromagnetic force between each other because they cannot repel or attract each other. That can be only between electrons or protons, right? So we're talking about nucleus, so we will only consider protons. So therefore, these are the particles, which are photons, which are responsible for the mediation of the electromagnetic force between two protons, i.e., we can say the repulsion between two protons is happened through these virtual particles, okay, between two protons, or in general, we can write charged particles, okay. Question number 2. A tube contains a vapor of mercury atoms at low pressure. In an experiment, the vapor is bombarded by a beam of electrons. An electron in the beam gains 6.7 eV of kinetic energy by moving through a potential difference V. Deduce V. Okay, so what is the kinetic energy that your particle is having? 6.7 eV, right? And how much is the potential difference that you have to accelerate? So it's very obvious that if you want to accelerate something in here, right, like that, so this is positive, this is negative. Okay, so if you want to accelerate something from positive to negative, of course, you need to apply some energy here, some potential difference here. Therefore, it will accelerate and gain some kinetic energy. So that mercury atom is actually accelerating here, okay, and gaining some kinetic energy. So that kinetic energy is coming out because of this potential, because the definition of voltage is work done per unit charge, right? And charge here is kinetic energy of the atom. So we will just write, and that is actually electron, right? So for the electron, it will go the opposite, not like this, positive. So the electron will be coming the other way. So that work will now be equals to kinetic energy, and that charge Q will be equals to electron because you're being bombarded by the electrons. And that 6.7 eV is actually your energy, right? So 6.7 into 1.6 into 10 raised to the power minus 19, you have to convert it into joules because voltage is joules per coulomb. Okay, volts means joule per coulomb, not EV per coulomb. So you need to convert the given energy, which is equals to kinetic energy, into joules, and for that you need to multiply it with 1.6 into 10 raised to the power minus 19. And what is charge here? Charge here is 1.6 into 10 raised to the power minus 19. That can be cancelled with this. So the answer to this question is 6.7 volts. Okay, so therefore the option is 6.7. Calculate the wavelength of the emitted photon of this ultraviolet radiation. Okay, so it's a very simple question. You will just write kinetic energy, or E equals hc over lambda, right? And what is the energy here? The energy is 6.7 eV, which we have to convert into joules again. What is h? Which is Planck's constant, 6.63 into 10 raised to the power minus 34, and c is speed of light, which is 3 into 10 raised to the power 8. And you need to find the wavelength. All you need to do is just to rearrange and get the answer as 1.8 into 10 raised to the power minus 7 meters. Okay. 2.3. The experiment is repeated with a different gas. Show the three lowest energy levels for an atom. Figure 2 shows the three lowest energy levels for an atom of the gas. Energy B, energy A, and ground. When an electron in the beam collides with gas atom, 18.4 eV of energy is transferred to the atom. The atoms subsequently emit a photon of visible light. State and explain the energy transition that are involved and support your answer with calculations. Okay. So first of all, you have to know what is happening here. Okay. So I need to write. Okay. Electron is coming and strikes the atom. Okay. And when it strikes the atom, what happens? And transfers energy of 18.4 eV okay, to atom. Then what happens? Once the atom has absorbed this energy, of course, it is going to excite, right? The atom is excited to state B. Now, why would I say B? Because the difference between 21.56 and 3.16 is 18.94. As the difference between ground if you like subtract them, you get the answer as 3 minus 3.16. Okay, so the answer is about. Okay, therefore it will move to the B. Now, after some time, the atom de-excites and return either to A or ground state and emit the visible light photon. Now, which level, I mean A or ground, the atom is going to de-excite. For that, we have to calculate for both. So let's check. We have to check now where the atom will go to release visible light photon. Okay, for that, we will say the energy that atom has hc over lambda, which is 18.4. Okay, and we have to convert it into joules. 1.6 into 10 to the power minus 19 equals 6.63 into 10 to the power minus 34 over into 3 into 10 to the power 8 over wavelength, and you are going to get it to be equals to 67.5 into 10 to the power minus 19 meters. Of course, this is not in the visible, this way, visible light wavelength range is visible light. Oh, my pen is not. Visible light wavelength is from 400 to 700. Therefore, we'll say not in visible region. Okay, so it means the visible photon is not going to be emitted when the atom is going to de-excite to the ground state. We were doing it for the ground. No visible photon emission. Okay, my apologies, I'm going out of the margin lines. Now let's check for A. For that, let me change the color for state B to A. This was from B to ground. Okay, so again, you will calculate the value for wavelength. Okay, and you have to check the difference between the energy level of B to A, right? For that, you have to do this EB minus EA. And what is EB? 3.16 minus minus 4.96. That will turn out to be equals to, let me get my calculator. 1.8 EV. So we will just write here now 1.8 into 10 to the power, sorry, 1.8 and then we are going to convert it into joules. 1.6 into 10 to the power minus 19 equals 6.63 into 10 to the power minus 34. And then speed of light, which is 3 to 10 to the power 8, okay, and divided by wavelength. So after doing the arrangements and calculation, I'm going to get 690 nanometers, which is exactly in the visible spectrum. So it means the atom de-excited from B to A and emitted visible light photon. Okay. Question number 3. Figure 3 shows a guitar with only one of its strings attached. The string is fixed at X and Y. The string is plucked and vibrates freely between X and Y. The distance XY is 648 millimeters. The frequency of the first harmonic is 147 Hertz. Calculate the speed of the wave traveling in the string. So for first harmonic means this is what we have here, right? And the length from here to here is called L, which is 648. And for standing waves, we know that L is actually equals to half of the wavelength. So wavelength is 0.648 meters. I'm just converting 648 millimeters into meters. Okay. And from here, you're going to get the wavelength to be equals to, let me calculate that. 1.296 meters. Okay. So F, which is given here, is 147 Hertz, and they're asking you to find the speed. So the speed is simply V equals F lambda 147 and 1.296, and the answer is 190.5 Hertz. Oh, sorry, meter per second. We were finding out the speed, sorry, meter per second. Okay, the tension in the string is 71 Newton. Calculate the mass of the string between X and Y. Okay, so the speed formula is actually T over mu as well. We know that, right? So what was the speed here? The speed here was 190.5 equals tension is 71 over mu, right? So taking square on both sides, it will be like this. Okay. And upon finding out the answer, we are receiving, or we are getting about, let me calculate, 71 squared divided by 190.5. Divided by 90.5 squared. That is 1.956 into 10 to the power minus 3. Okay. Now you got mass per unit length. This is actually called mu, or mass per unit length. And now you have to calculate the mass. So mu is actually mass per unit length. And what is length? Length is 0.648 meters. And mu is 1.95 into 10 to the power minus 3, right? Kilogram per meter. So we are just putting in the values. So 1.95 into 10 to the power minus 3 equals m over 0.648. And after dividing or multiplying, I'm going to get about 1.3 into 10 to the power minus 3 kg. Okay. So the sound produced by the guitar is analyzed. The sound is superposition of the first harmonic F1 with harmonics F2, F3, F4, and F5 of the stationary waves that exist on the string. Figure shows the frequencies of these harmonics and their relative amplitudes. Draw on figure 5 the stationary waves that produce the harmonic F3. Label the positions of all nodes N and antinodes A. Node and antinodes. Okay, so F3. F3 means you have to make a trifold, okay? Because you should know that we have the formula, a general formula here for the N harmonics. For N harmonics of standing waves, Fn equals NF1, right? So F3 means 3 times F1, right? And 3 times F1 refers to actually just 3 into the frequency of the first harmonic, which is 147. So when you multiply 147 into 3, 441, As you can see in the graph, we have about 441 here. You can see 441, okay, for the third harmonic. So of course we are going to have three three cycles. So 1, 2, and 3. Okay. Make sure that the amplitudes are equal above and below, otherwise they will cut the marks. They are like AQA is very dangerous in this, so you have to be very much careful with making. Oh, I'm not good at making them. Okay. Okay, that's like better. Still no good. The amplitude above and below should be same, otherwise you will lose marks. Be careful with that, okay? So the points here are notes, and the points here are antinodes, right? Because they ask you to make for F3, so for F3 you will only have 3 trifolds, okay? Okay, 3.4. The string is vibrating freely. The player then touches the string lightly at its midpoint Z, as shown in figure 6. This prevents the string from vibrating at Z. Okay, so when the string is preventing to be vibrated at Z, it means that point is your node. The sections X, Z, and ZY of the string continue to vibrate. Okay, here it is. The sound produced by the guitar is analyzed. Okay. Deduce with reference to frequency how the harmonics present in this sound compare with the harmonics present in figure 4. So first of all, when you have some kind of disturbance here, it means it is your node. No wave is here. Then in this direction, we will have standing waves. And in direction, we will have another set of standing waves. Okay. Now, you can see that for this portion and for this portion, the length has been divided into half. Okay. So when the length has been divided into half, we can say that the frequency is actually equals to V over 2L, right? Or in other words, we can do the calculation here. F equals V equals F lambda. Since V is constant here, so we will just write F equals V over lambda, right? And usually we know that the length is actually equals to half of the wavelength for one complete harmonic. Okay, so if this is your length, then this is your half of the wave. So half of the wave equals length. But from here you get lambda to be equals to 2L, right? So you have the answer like V equals 2L because you're just putting 2L as lambda. Okay. Now this was for your previous case when you had the length, previous frequency. Okay. When your length was 0.648 meters. Okay. Now what have you done? Now the length is halved. Okay, halved. How? 0.648 is reduced to 0.324. So that means we know that F is directly or inversely proportional to length. So if length is halved, then frequency is going to be doubled, right? When frequency is doubled, F1 previously was 147 hertz, previous, the frequency of first harmonic, okay? So the frequency of this harmonic or now will be 2 times 147, 2 times 147, that will turn into 294 hertz now, okay? So we can say now previous harmonic series was F1, F2, F3, or you can say rather F1 equals 2F1, you know, Fn equals Nf1. So I'm just putting for 2 equals like F2 equals 2F1, something like that, okay? And so on. But now what kind of Cs you have? Now you have everything doubled. So your first one is 2F1, not simple F1. And your 2F1 is actually turned as 4F1. And your 3F1 has been turned into 6F1. And your 4F1 has been turned into 8F1. So if you notice that the frequency of harmonics, like only even, you only have the even harmonics available, i.e. when string is plucked at the center, then even harmonics are produced. Okay, and odd harmonics which were there before, if you can see in previous case it was F1, F3, odd harmonics were there, and now odd harmonics have been disappeared. And it was not possible for the odd harmonics to be here. Okay, so this is actually they were asking that when you pluck the string in the middle, what happened to the frequency of harmonics? So previously it was F1, 2F1, 3F1, 4F1, but now when you plucked it at the center, the new frequency is now double of the length. So 2F1, 4F1, 6F1, and 8F1, and so on. This was the new series of harmonics. So you will just say the frequency is doubled and the new harmonic series is only even harmonics, no odd harmonics. That's it. Question number 4. In this question, assume that all forces are coplanar. Okay. I mean, those forces which are acting in one plane, for example, in XY plane, not going into Z plane. So figure 7 shows a car that is traveling at 25 meters per second at a distance s from the traffic lights. The driver applies the brake so that the car and trailer stops at lights. The car and trailer undergo constant. Remember the word constant. So when you have a word like constant, it means you can use SUATs, right? Which means equations of motions, right? So when you reach the signal, of course, your speed will be 0, right? So your final initial speed is u. So I want to know the distance s. So for that, I have initial speed, final speed, and I want to calculate the distance. Okay. So for that, I'm going to use this third equation of motion, which is third SUAT. So 2as equals v square minus u square, or acceleration, which is actually deceleration. So I'll put this with negative because it is deceleration. Okay, not acceleration. When your speed is reducing, it is called acceleration, but in negative, or in other words, deceleration. And when your speed is increasing, it is acceleration with positive sign, which refers to speed is increasing. So final speed here is 0, and initial speed here is 2.8 meter per second. Okay, and we need to find s. So simply 2as equals v square minus u square, and s equals 0 square minus minus 25 over 2. The value of is 2.8. Oh, my apology. This is 25. Okay, so the final answer to this is, or you can round it off to 112 meters. Okay. The car and trailer accelerate from rest along a horizontal road. Figure 8 shows that the car exerts a horizontal force PH on the trailer, which is actually the pulling force. And when you pull the trailer, it is actually moving on the road. The trailer has a weight of 2,500 Newton. The reaction force R on the wheels of the trailer is R. Initially, there is no resistive force on the trailer, and the trailer accelerates at 1.5 meter per second square. Calculate the initial value of PH. Since they are telling you, since initially no resistive force is there, only accelerating force, okay, right, which is PH. So we may use Newton's second law of motion, which is F equals ma, and F is actually here PH, and m is actually equals to W by G, because your mass is not here. The trailer, the acceleration is being produced in this, right, in this object, so we have to consider its mass, right? And the acceleration is 1.5, so PH equals 2,500 divided by 9.8 into 1.5, and answer is going to be 382.7 newtons. Air resistance D acts on the trailer when it is moving. Okay. D increases as the velocity of the trailer increases. Figure 9 shows how D varies with V. Figure 10 shows the forces acting on the trailer when it is traveling at a constant horizontal velocity. The car exerts a vertical force PV, okay, and a horizontal force PH on the trailer when it is traveling at a constant horizontal velocity V1. An enlarged view of PV and pH. PV means vertical force and pH means horizontal force is shown in figure 10. The horizontal force pH is now greater than the value calculated in question 4.2. The vertical force PV is 762 newtons. The resultant force of pH and PV is 912 newtons. Determine V1. So what is V1? You have to calculate the V1 from this graph. And for that, you have to calculate drag. And in order to calculate drag, you have to use pH and PV. So first of all, if you can take a look of this diagram, we have a force pH and PV. And pH is actually acting like this. We need to use head to tail rule. Okay. So this is pH and this is PV. Okay. And the resultant force is this one. This is resultant. Okay. So resultant is 912 newtons and PV is 762 newtons. And this is what we need to find now. Okay. So according to Pythagoras theorem, we have 912 square equals 762 square plus pH square, right? And from here, pH is going to be, let me calculate that, 501.1, okay, rounded off to 501 newtons, okay? Now, it is very important to know that they are telling you here something, that the car is traveling at a constant horizontal velocity. So it means, since car is moving at constant velocity, it means sum of forces, sum of horizontal forces are zero, right? So you will write leftward forces equal rightward forces. So leftward is pH and the rightward is D. So both of them are equal, right? So we will just put the value pH here, which is 501, and it should be equals to D. Okay. So 501 newtons is your D. Now look at the graph for D equals 501 newton to find V1. And when we do that, 500 is here. So 501 is here exactly to be equals to 10. So our answer to this is 10 meter per second. Okay. Okay. D can be considered to act at the position shown in figure 11. Okay. For some of the forces, the distances of their lines of action from the center of the trailer's wheel have been included. This is the center of the wheel. Okay. That is the pivot, you can say. Okay. This will be our pivot. Okay. Explain why PH has no movement about the center of the trailer's wheel. So you can see that the line of action of PH is passing through pivot point, right? And whenever the line of action of a force passes through the pivot, its moment becomes a zero. Okay. Or you can say, in other words, that this PH is actually parallel to the moment arm, and moment is actually equals to what? Moment means R and F. They have to be perpendicular to each other, right? Either moment arm is perpendicular to force or either force is perpendicular to moment arm. So moment arm here is actually this one and force is actually this. And you can see that both are parallel to each other. So angle between them is theta. So RF means RF sine theta, which is RF sine 0 because they're parallel. So the moment will become 0. Okay. But in Mark's theme, it is mentioned that you should not write parallel and this will remain insufficient. So you must write this answer that I'm going to write now, that since the line of action of force PH is passing through the pivot, which means that angle between moment arm and force PH is 0 degree, right? Therefore, the moment due to pH will be 0. When the car and trailer travel with velocity v2, PV is 0. Determine v2. This is again very important question. And for that, I have to draw the diagram. Okay. So now this is your D. Okay. Or let me go back to the given diagram and let's work out with that. Okay, so in this diagram, you can see that the line of action of D is going like that. Okay, so we can say that the D is acting at this point. Okay, so this point and this point. So that is your moment arm R and that is your force D. Okay, so R into D, they are at 90 degree to each other. It means moment arm R and D is perpendicular to each other. That is perfectly making a moment. Now, secondly, the weight is acting down. Okay, so for that, let me use another color. So from here, it's coming gray and the weight is moving down like that. Okay, and you can see here that the angle is 90. So now moment arm here is R and W is force. So R into W. Now, what kind of moment is created by the weight? So how do we know? This weight has to be turned towards the pivot and like that. So it is anti-clockwise. Okay, this is anti-clockwise. And for D, how do we know? Just shift that towards the pivot. So it is clockwise. Okay, clockwise moment. Yeah, clockwise. So you will write like that. Now that we have the values for all, anti-clockwise moment will be R, which is R, which is 0.8 times force, which is 2500. Okay, and here anti-clockwise moment will be force, which is D, times its moment arm, which is 0.95. Okay, so that is your clockwise moment and anti-clockwise moment. Now what we need to do, we will just write clockwise moment equals anti-clockwise moment, right? And our anti-clockwise moment was 0.8 times 2500. And our clockwise moment was D into 0.95. From here, I'm going to calculate D to be equals to 2105.3, which can be rounded off to 2100 newtons. Okay. Now we'll look for the graph again for D equals 2100 Newton and find velocity V2. So let's go back. There it is. So 2100 is actually here, right? And 2100 is giving me about this value, which is 20.5 meter per second. So V2 is 20.5 meter per second, right? Therefore, I will write the answer as 4.6. The air resistance, the air resistance D acting on the trailer increases as the velocity V of the trailer increases. Explain this increase in D with reference to the momentum of the air displaced by the trailer. You should also refer to appropriate Newton laws of motion. Well, you should know that F is always a drag force, FD or D, because here it is given as D, so I will write just D. It is directly to V. So greater speed of the trailer means greater is the drag force. Why? Because we will write now as point number one, as trailer is moving fast or at high speed, it is displacing more air is displaced by the trailer, right? And in order to displace more air, more energy and more force is required, right? For displacing, sorry, because you can say that the large amount of air is coming and hitting the trailer and the trailer is pushing it back or pushing it off. So more and more volume of air is coming and striking and more of the volume is being put off by the trailer. So it means more force is required to put off all the air. Therefore, we will say drag is increasing. So as trailer is moving fast, more air is displaced by the trailer, which is coming and hitting, which is striking the trailer body. Okay. So now you will write for removing more of the air, more drag force is needed, more force is needed. Okay. Now, when more force is needed, it means more change in momentum, right? Therefore, change in momentum will be more. How? F equals ma, and you know that a is actually equals to vf minus vi over time, and you know that vf minus v actually change in time, and t can be written as change in speed, change in time, and m delta v can be considered as change in momentum. So you can write F equals ma as F equals change in momentum, right? So now you can see that they're both are directly proportional to each other. This rate of change of momentum, delta v over delta t, is directly proportional to F. So if F is increasing, it means rate of change of momentum is also increasing. Okay, that is actually referred as second law of Newton's, right? And we can also refer to third law of motion. So we will write when when air is coming and hitting the trailer, it is like doing some action. So the same amount of action will be done from the trailer on the air as well, right? Air is coming, hitting the trailer, that is action. And trailer is also going to hit back to the air with same amount of force but in opposite direction, that is reaction. So how would you write it? So write greater force, when greater force is exerted by air on trailer, which is called action, maybe. Okay. Then in reaction, the trailer put or exert the same reaction force on trailer. That is actually referred as Newton's third law. Okay. Let's move on. 4.7. The car has a maximum power output of 95 kilowatts. The maximum velocity of the car and the trailer is 25 meters per second. At this velocity, the force D on the trailer is 3100 newtons. The car exerts a horizontal force PH on the trailer, and the trailer exerts an equal and opposite force of magnitude PH on the car. Assume that the air resistance and pH are the only resistive forces acting on the car. Calculate the air resistance acting on the car when it is traveling at a constant velocity of 25 meters per second. Okay. So for that, first of all, what you have the power output, which is 95,000 watts. Okay. And you have the resistive force of 3100 Newton at this point, right? At this force. So what are you going to do now? You will just write wait. Okay. So first of all, you have the drag force 3100 Newton, and the speed you have is 25 meter per second. Okay. Now there's a trick here that the drag force of 3100 should not be used here. Okay. We have to rather calculate the drag force using the speed, the max speed. The max power is this. This is max, and the V max is 25 meter per second. Okay. So what kind of resistance that we have here? So P equals work over time. We know that P equals force times displacement over time, right? And force times displacement can be written as S over T, and S over T can be written as FV, right? So now power is 95,000, F to be found, and V is 25. Okay. When we calculate that, it is going to be 3,800 Newton. Okay. So it means the car is applying this force. It means the car is applying 3,800 Newton pull as PH on the trailer to move it at 25 meter per second. Now that is an accelerating force. So it is an accelerating force, right? Now what about decelerating forces? The decelerating forces are, first of all, drag, which is 3,100 Newton, and the other one is air resistance. This is what we need to find, right? So as the car is moving at constant speed, as velocity is constant, so leftward forces equals rightward forces, correct? And for that, leftward force, which is accelerating, it is 3,800. And the rightward are decelerating, which is friction air resistance. So D plus air resistance. So 3,800 equals 3,100. It is given in the question, and air resistance AR. And from here, AR to be equals to 700 newtons. Okay. Question number 5. Figure 12 shows a circuit for controlling the current I in the filament lamp L1. The battery has negligible internal resistance. Figure 13 shows how the resistance of L1 varies with I, okay, with current. The current in L1 is increased from 0 to 0.50A. The potential difference V across Li is 0.375 when I is 0.50A. Draw on figure 14 a VI graph for L1 in the current range 0 to 0.5A. Okay. First of all, you should know that R is equals to V over I. It means if I find the gradient of graph V and I get a constant gradient, then it shows that the graph is straight line for VR, right? Now, if you take a look here, from 0 to 0.5, this region, you see this is R and this is I, right? So the resistance here is constant, right? Resistance is constant. And when resistance is constant, means we will say the gradient is constant, right? And when gradient is constant, what kind of graph we have? Straight line graph. So we have to develop a straight line graph of V and I all the way from 0 to 0.5 because it is given, and from 0 to 3.75. So you will just go up till here, and from here, this is the point, and you will just do like this. Okay. Calculate the power dissipated in L1 when I is 1.9. Okay. Oh, what happened? Okay. So 5.2. Calculate the power dissipated in L1 when I is 1.9. Since you should know that all of them are connected in series, can you see? So the current here and here will be same. So the current here is 1.9 and current here is 1.9 as well. Okay. So for this question, I will just write V equals IR1 plus V equals IR2, correct? Okay. Now what is V? 9. What is I? I is considered taken as common. So R1 is actually considered as RL plus R2. Okay. And they have given something here? No. 1.9A, and 1.9A is referred to 1.6, 1.7, 1.8, 1.9. So 1.9 is moving all the way up till here, 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 and then here, right? So RL is going to be 3.6 ohms because this resistance is for L1, lamp 1, not for R, okay? They have written that the resistance of lamp 1 is this. So RL is going to be 3.6, right? So 9 equals 1.9 equals 3.6 plus R2, right? So from here, after some simplifying, oh, I think I made a mistake. Just hold on. Oh, okay. Have they given some resistance here? So R2, okay, let's find out. Let me calculate that. 9 divided by 1.9. This is going to be 4.73 minus 3.6, 1.13. So, okay. Okay, never mind. My apologies. I have to change it. So we'll just look for the power dissipation in lamps. We will only consider the power dissipation in lamp. So for that, what we need I and R. And from graph, simple as this, from graph, I equals 1.9A, and for that, RL equals 3.6 ohms. Okay, so P equals 1.9 square, and R is 3.6. So power dissipation is going to be 13 watts. Okay. 5.3. The variable resistor R in figure 12 is adjusted until I is 1.5 ampere and V is 3.3. Calculate the value for the resistor R. Now that was the question that we have done before. So we will just write V equals IR1 and V equals IR2, and that is actually your lamp resistance. So V equals I, right? And when I equals 1.5A, RL equals, we have to go back and see. So when I equals 1.5, RL equals 2.2 ohms. Okay, so this is 2.2 ohms. 2.2 ohms, right? And V is 9 volts. So a 9 equals 1.5. RL is 2.2 plus R2. And from here, R2 is going to be 3.8 ohms. Figure 15 shows a second lamp L2 and L1 connected to the circuit. R is adjusted so that the potential difference across L1 is again 3.3 volts. Reduce without calculations the change in the resistance of R. Okay, now you have two lamps. So it means the current which is coming here and moving here, for example, from here it is coming I and now it is moving here I1 and moving here I2, because in parallel we know that the current divides. So in order to illuminate or power the two lamps in an equal way, the current has to increase, right? And when the current is increased, I1 and I2 will increase, and when they meet up here and come up here, we will have I1 plus I2 together, right? As a result, we will see that the total current I is increased. And when total current I is increased, it means this R should decrease in order to follow or in accordance with Kirchhoff's voltage law. Okay, so here's the answer. How would we write? Okay, since L1 and L2 are connected in series, sorry, in parallel, are connected in parallel. So the voltage for L1 and L2 will remain same. However, the current will rise in order to illuminate lamp 1 and lamp 2 equally. Okay. Now, we know that R equals V over I. So we are saying, of course, V is kept constant, it's not changing. So in order to illuminate the lamp 1 and lamp 2 more, we will say R total for lamp 1 and lamp 2 is reduced because they're connected in parallel, okay? Parallel combination. And when R is reduced, I increased. So I equals I1 plus I2 increased, okay, in lamp L1 and L2, okay? And when they combine, when reaching variable resistor R, I equals I1 plus I2 will be enhanced. It will have a greater value. Will have a greater value, right? So R equals V over I means I increased, so R decreased, right? Therefore, R must decrease. And which R? This R, okay? Figure 6.